Okay, in this video, I'm going to talk about system identification of a motor, which becomes useful when you maybe don't have your data sheet available to you here. Why don't I get a marker? Okay, so system identification is a fancy word to say measuring parameters. In this case, we're going to look at how do we measure R, this motor torque constant K, and then also TC if we care about efficiency. And what we're going to do for this example, we're going to assume B is equal to 0 for simplicity, and we'll leave it as an exercise with a slight guidance for how you might figure out the value of B if you wanted that as well. Simplest approach is the following. You would use a few simple tools that are often available at an electronics workbench. So first of all, you would measure R using an ohm meter. And make sure to average over a full rotation. Because the resistance can vary depending on commutation. Next, you will measure free running current. Call this IF using an ammeter. You may need a pretty sensitive one, or depending on how big of a motor is, or you might need a very large one to measure large currents going through that motor. And the last one is to the free running speed. Omega F. Using, there's a couple ways to do it. Easiest is a tachometer, which is a special device that if you put a mark on the axle, it will pick up as that mark passes in front of a light. It's also possible, if you don't have a tachometer, if your motor is not spinning too fast, sometimes you can do it with a high-speed camera, like a cell phone actually. And then record how fast, how many frames it takes for the axle to rotate around like this. Okay. And then in both of these cases, just a remark, for 2 and 3, motor must be driven at a known voltage. Let's call it Vs here. Okay. All right. So now, how do we, once we have these quantities, how do we calculate our system identification. So we do two things. First of all, we assume all of the torque output Tm is consumed by by Tc, this Coulomb drag. Therefore, we can conclude that Tc is equal to K, this motor torque constant, times this free running current that the motor consumes when it's spinning. So the motor out, the magnetic torque Tm is equal to Tc here. So Tm is equal to K times If equals Tc. Okay. Then we can use, let's see, which equation is this? I don't remember which equation from it is, but from above. We have that our definition of omega f equals 1 over k squared plus br times kvs minus rtc. This is from the definition of omega f above. So we're assuming in this case that our b is 0, so we can neglect this term, the denominator. And we can do some rearrangement. And we get that k is equal to vs minus if r over omega f, where we have also used this equation in here to replace Tc here. Turns out the k drops out here. So we have this relation for k here. And then we use this one here. Okay. Let's do an example here. Uh, 4mm motor, a little tiny motor. Measuring the resistance across the terminals using a ohm meter, we got it was 4.6 ohms. Measuring the current when the motor was spinning freely at we got at 4 volts. We got that it was 63 milliamps at 4 volts. And using a high-speed camera, we got that the free running speed was 78,000 RPM. Now, RPM is convenient for recording videos and things like that because it talks about rotations and minutes and things like that. But our omegas, the math we've been doing has been in radians per second. So we need to convert that to radians per second. So that equals 78,000 times 2 pi over 60 radians. Like that, okay? So if we plug these numbers now into this equation, first of all, we'll do this equation because we need to find k before we can get the Tc here. So we know Vs is 4 volts. We know If, we know R, and so on like this. So we can get the following, which is that k is equal to 0.45 micronewton meters per amp. So that's give it an amp and it produces that much micronewton meters. Of course, if you gave it a whole amp of current, it would burn out this motor very quickly. These motors use much less than an amp. But if this is the relation between current in and torque out, that motor torque constant. And we can also calculate this Coulomb drag friction on the bearings, and that turns out to be a very small quantity, but relevant nonetheless. 2.8 times 10 to the minus 8 Newton meters. Let's see, what is it? Newton meters. That's it. Okay. And that's right. Newton meters is a measure of torque. Okay. And then with that, we can, if we want to, play some of these, use some of these other pieces of equations we derived above. We can get that. We can find out, for example, the P max. That turns out to be, for this little motor, 0.75 watts at 39k RPM, which is half that speed. And then eta max for this motor, peak of that eta max is at a different RPM. It's this one here. Eta max is, max efficiency is 53%. And that happened at higher RPM, 61k RPM. Okay, so that's an example, and we can calculate some of these key quantities. And then if you basically type all these equations into Python, you can derive what that torque speed curve looks like for this motor. And this is what it looks like. Here's that angular velocity, omega. Here's the efficiency here, peaks at about, about 50%. Here's a power curve, looks like an inverted parabola, peaks at half the torque, half the angular velocity. And then here's this blue line is actually the current going into the motor, and you can see that it has, it's a non-zero at this high RPM. It jumps up because it's dealing with this Coulomb friction. All right. And if you look at a manufacturer's data sheet that actually provides these torque speed curves, you'll see something that looks a lot like this for commercial motors, DC motors like this. Okay, lastly, so the question is maybe, once you know this is a torque speed curve of a motor, how do you use it? And what this tells you is a few things. One way that you can use it, and note this is the steady state behavior. This doesn't say anything about the acceleration you would see when you first turn it on, but it does tell you about the steady state behavior. So for example, one way you could use this torque speed curve is you could say, well, maybe I have a load like a pump, for example, that has a fixed torque. This torque speed curve would tell you, like suppose I have a torque of 200 micronewton meters that is loading my motor. This torque speed curve would tell you how fast the motor would spin. Maybe you've got a propeller that's got a certain amount of drag. It would tell you where you would land on this torque speed curve. Conversely, if you wanted a specific RPM, 50,000 RPM, it would tell you how much torque load you would need to apply to the motor to get that RPM. And actually, in principle, if they don't match perfectly, you can change your voltage up or down, which will move this torque speed curve up or down, and move these other curves as well around too, to get kind of an operating point you want. But of course, do keep in mind, as you crank up the voltage, you crank up that dissipation through the coil, which does depend on voltage. And so you have to be wary not to burn out your motor, especially way over here. For example, if you stall your motor, it will draw a lot of current, and it will burn out quite quickly unless you have some very good cooling on that motor. And then the other way you might use this plot are these analyses here. This is for steady state, but the other thing you might want to do is maybe you want to do feedback control of the motor, for example, with a PID controller. And essentially what you do to do PID control is you need a model of your plant. And you have now the tools, through system identification, for example, to derive a plant model. And what you would do to derive that plant model is you would take this, this full model at the beginning of the motor, and you would add in a model of your load, which is intimately connected to this. For example, if your load was an inertial load, it would look like another capacitor here in place of this load. Or if it was a drag load, it would look like a resistor, for example. And then you'd use your circuit analysis techniques to calculate what the transfer function would look like from your ideal source here coming out of your controller. You'd have an output, maybe your angular velocity, for example, would be a reasonable output you might want. And that would, from that, you would generate a frequency domain transfer function that you would use to design your PID controller, for example. So that's the other way you could use this, is you use this full model, or maybe this reduced steady state model if your dynamics are slow relative to your inertia, to derive a transfer function. Okay, and that concludes the video.